Okay, I think we were about time. So Eden, why don't
Mm,
you start because I probably have like a minute or two introducing the smart project as well. So
okay. Okay, welcome everybody. Thank you all for coming to our Smart Talk today. Today, Dr. Rob Redmond will be speaking, and he is a senior scientist with NOAA's National Centers for Environmental Information, where he serves as the lead for both the NOAA Center for Artificial Intelligence and the Space Weather Follow-on Science Center. So Peter, you can introduce our SMART project.
okay, so before we hand the floor to Rob, just want to say a few words about the SMART project. SMART is a ground-based magnetometer network project sponsored by NSF. UCLA has been building ground-based magnetometers for making space weather observations since 1990s, and even earlier than that for a couple of more earlier efforts. UCLA students have always been a part of these efforts, even though they were mostly behind the scenes. When the SMART project began in 2020, the COVID pandemic just started for a few months, and lockdowns and restrictions made a serious impact on the educational opportunities for our students. The SMART project decided to include many more students on the project than originally planned, in response to a national call for supporting our next generation scientists and engineers. We greatly appreciate NSF and the CalSpace Consortium for their support to these students. We're also fortunate to have attracted many talented and highly motivated students in this one of the best universities in the nation. Their passion motivated us to create Smart Talks. These are TED Talk-like presentations by external experts in space science and technology. And Smart Talks are about what inspired these experts to do what they are doing in their careers. Smart Talks about space science and technology in action. We're grateful that the newly founded UCLA Space Institute for spreading the word of this event. I'm privileged to have worked with our distinguished speaker today, Dr. Rob Redmond, on the magnetic waves at the geosynchronous orbit observed by NOAA satellites. And I want to thank him for spending his precious time to speak to us today. So I'll give the floor to Rob.
Hi, well, I'm honored. I feel very lucky to be here. Thank you so much, Peter and Eden. I really appreciate this opportunity, and thank you all students for coming. And I hope you have some good questions, and maybe we'll foster some collaborations down the road. So I'm Rob Redmond. I didn't put my email address there, but it's rob.redmond@noaa.gov. I lead the NOAA Center for Artificial Intelligence, and I'm really excited to kind of share with you what we're doing. So let's go to the slide. There we go. Okay, so I'm trying to make this a little bit fun. I do have a lot of slides here. I promise to make a copy to make available to anybody just after the talk. So I wanted to share, a little bit of my journey. How did I get where I'm at, and then spend all the time on all the cool stuff we're doing at NOAA. It's one of those things, like I really, really love what I do, and I'm excited to share that with you today. So there's a QR code there. You can get to our website. It's also super easy, noaa.gov/AI. And let's just go into it. So, all right, a couple of pictures of me through the years, in a sense. When I was a kid, probably just like a bunch of you, and I used to stare at the TV. Back then, the TV was really big in one dimension and really small in terms of what you could see. And I used to stare at it and watch the space shuttles take off. And for hours, honestly. And I got a chance to go to a NASA space camp. I was in Huntsville, Alabama when I was in 6th grade. And it really like cemented my my enthusiasm for science, technology, math, engineering, all those things there. I've had a adventurous route, if you will. And I'm really so glad that it ended up working for NOAA. I've been there almost 20 years. I'm in Boulder, Colorado area, and you can see my love for the, I found my professional home at NOAA, right? And as mentioned in the intro, I had the honor of working with some really brilliant people to facilitate their work and lead the NOAA Space Weather Follow-on Science Center, as well as the Center for Artificial Intelligence. As you can see, I love spending time in the outdoors. Got to give my wedding vows at the top of Kilimanjaro. It was really windy, so I'm not sure if Daria was able to hear me, so I also wrote them down. If you ever get a chance, such a beautiful place to go visit that, in general. And then we have a 2-year-old almost in about 2 weeks. Our only daughter will be 2 years old, and we're already introducing her to what we're passionate about outside of the work environment. All right, so what do we do? So we're kind of a center of excellence concept. We don't have a building. We are across NOAA. NOAA is a place that you may not have a ton of familiarity with, but you probably use NOAA data every day. So if you check the weather, or you look at climatological information, you're probably interacting with a product that traces to NOAA data as an important aspect of that product. So we are across NOAA, sun to bottom of the ocean floor, center of excellence group that is trying to improve our ability to forecast and predict weather and climate, as well as improve our ability to observe all the ecosystems. So we do that. What's our mission, right? We're trying to proliferate the use of trustworthy AI at NOAA by basically building a community of practice of people interested in NOAA and outside of NOAA, perhaps like yourselves, to bring your brilliance inside so that we're producing the best things for public good. What's the call to action? What gets us, why are we doing this in a sense, right? So this is a graphic of from 2021, 2022, looks unfortunately similar, of the numerous unfortunate $1 billion natural disasters every year. So those, along with climate-driven impacts to our coasts, our oceans, our ocean ecosystems, and the oceans are important both for the fish of the sea, but also that's an important source of food for the planet. That really motivates us to take advantage of modern technologies. So really getting our data usable and out into the cloud and available to everybody. So it's not just on a shelf somewhere or on somebody's research computer. It's a good place to start. We want to get it out there to everybody. Take advantage of uncrewed systems. So these are drones in the ocean, drones in the sky, to observe places that are hard for humans to go and observe, and artificial intelligence to really get the most out of the data, so we can produce the best insights and tackle these complex problems. And kind of bringing it home, it's kind of in a way I always find you really understand what communities go through when you become a community that went through a natural disaster. And these pictures are pictures from my hometown in Louisville, Colorado. About a year ago this time, we had just an out of control fire. And it's an example of the kind of where that natural environment, like the open space, the urban environment where we live, intersects. We had winds of over 100 miles an hour. It was in January. And so you can see, normally I live in a place with a fair amount of snow. So this really brought it home to me, and it just, it brings it home to everybody. And we were all doing fine, but this kind of thing really affects communities for decades. So that's my sense of urgency. Now I'll show you some cool eye candy. Should automatically play. This is if you're following along separately, it's slide 6. But this is showing the use of AI to classify video imagery. We have tons of video imagery under the ocean. And a quick metric by the numbers is an hour of video imagery takes about 4 hours by a human to annotate all the important fish in the sea. Well, that's not tractable, right? That could work for a research project, but that doesn't work for, say, trying to find the salmon, find the sharks. We started with sharks. I, for one, would like to know where the sharks are. I want to avoid them. So that's an example of a technology that's being used at NOAA, and you can imagine lots of other opportunities for using classification systems like this. Go to the next place. All right, so we're trying to build a community practice. That's kind of a cool buzzword these days. There are already groups of people doing, as probably some of you are involved in groups doing AI for your research areas, and those exist. The thing that we recognize at NOAA, which has about 260 AI projects going on, and 2 years ago it was like 190. So 190 to 260 in 1 year. That's a pretty big increase in that number. And the recognition was there's all these really cool projects going on, and they're not sharing information. So think AI, there's limited transfer learning going on. So what we want to do is kind of just think of building a Slack channels and building places where people can come and ask questions, get help, and share code, share things that didn't work, especially with each other. There's a QR code on the top right. It's open to the world. You're welcome to join our community practice. Basically, we send a monthly newsletter. We are super hopeful this year to start building out Slack channels and workspaces, probably start inside NOAA, and then make it more accessible to the broader public, as we do during our yearly workshop. That's also open to the public. So mid to late September, we'll have our next AI workshop for NOAA. I'm going to share just a couple of things that we're doing. So we're building a few things, and we're trying to bring a lot of people together, and we're trying to get them to use those, we'll call them standards and guidelines. And then we're also funding a few pilot projects to show that developing an AI-ready data standard, what does that really mean, right? But to show that developing one has a lot of value, and that we're moving that the set of principles or guidelines in a direction that accommodates the sun to ocean floor data sets and model outputs that we have. So just to kind of sprinkle this a little bit, for example, we are working on creating a new humidity data set that would be at the spatial and temporal scale, that on what we call census track, or at the right, enough fidelity to be important for communities. When you add humidity and you add temperature and other factors, you can start to evaluate that community's response to heat exposure, for example, other things. We are working on creating a 22-year or improving the AI readiness of a 22-year multiple decade tropical cyclone data set, so that we can better understand as climate changes, how are the future tropical cyclones likely to look, and what are those impacts to the coastal communities likely to be like, unfortunately. We're also working on trying to improve our human ability to use data. So for example, automatically detecting potential problems in drone observations. So as your cell drone runs into an iceberg, first, you don't want that to happen, but if it does, probably maybe those measurements are ones you don't want to use until the equipment is functioning correctly again. So we're working on automating QC. And then I love this last one on the, well, two more, I guess. We're also working on looking at the peer-reviewed literature or peer-reviewed community like JGR, geophysics, and other peer-reviewed outlets as a way to, with natural language processing, as a way to trace the value of NOAA data, the value of our investments on the basis for the public. And then we're also working on a pilot project that is characterizing the soundscape of the ocean. That's water column sonar, so that we understand what the ocean sounds like. Very important for also understanding how to not overfish areas and understand the health of different species. I'll go into the two on the bottom right in a second here, actually right here. So, all right, so we're working with the community. We're trying to do this in a vacuum or in a cave. And we're working with the community to help us understand what do we need to do better about the data sets that we have, so that they're more usable. And so we're working with a group called the Earth Science Information Partners. They're a nonprofit. They're co-funded by various U.S. agencies like NASA, NOAA, and USGS. And they form facilitation clusters. They have monthly meetings and have a couple workshops And those clusters are generally open to anybody in the world who wants to be part of the community conversation. So on another slide, I'll have a link where you can join us if you want to. But really key is, what's the driving motivation here? You're not AI ready until you're, so I'd say until your workforce are trustworthy AI ready too. We conducted a survey through that EFIP collaboration group, and the outcome was kind of, as you can expect, unfortunately, that we spent a lot of time massaging data before we we see AI ready as not this totally new thing, but rather take a data set, maybe it's in NetCDF, maybe it's in bits files, imagery of the sun, and thinking about, well, what improvements we need to do as like a, so that it's more useful, right? And so we see the primary categories to be preparation, documentation, quality, and access. Those kind of make sense, right? Especially access. We still are in kind of today's paradigm where we're downloading a lot of data onto our laptops. It's really hard to find sometimes. It takes a long time to get it, and we don't usually have enough storage space. So that's still a fine paradigm, especially for smaller projects. But for these big problems, like looking at 22 years of tropical cyclone data and pairing that with societal, census, social, socioeconomic data, we have to get it to a place probably where we're going to be using cloud compute and storage, most likely, in order to address that research and those applications. So these are, what are the things that are specific to AI here? There are things like, has this data set ever been used to create a machine learning model and published? That'd be really nice for others to know who don't yet have experience with that data set. Does this data set have the fish of the sea labeled? Okay, cool. What species? Oh, it has halibut, but doesn't have salmon. That's also nice to have that next to the data set so that it's not something people stumble across. Maybe they want to do transfer learning from one kind of salmon to another, for example. So a lot of things like that. Oh, a key one is, does this data set have sample code I can go use? And is it sitting right next to the data? Usually you can usually Google for code snippets for various data sets, but that's not very easy to do. We want to make that easier. So we're working on making a library, and I will go to that next, I think. So that QR code there is going to get you to the group that's working on defining what it means to be AI ready for open environmental data. You're welcome to join us. Okay, so now you got a pile of improved data sets that are more AI ready. Maybe they're cloud optimized, really easy to get to. This is a graphic of kind of the data evaluation and application development lifecycle as we see it. So it needs to bring all the right people to the table, especially with AI, right? We don't want to end up with so-called black boxes that are hard to interpret, hard to explain, and then when we give this product to a target community, maybe they won't want to adopt it, or maybe they will wonder about the trust, or it's how can they trust it for use in making decisions about their community. So this is all about getting all the right people together at the beginning and keeping them involved in the process. Okay, that's the big picture. Okay, what have we learned we got to do right now? We have lots of AI going on at NOAA, 260 projects or so that are we're trying to get them to share more with each other, so that they can go faster, basically, and get to useful products quicker that are even more trustworthy and understood and less biased and things like that. So we recognize that we need to build a library, basically GitHub, Jupyter library that's public and open, that is basically available to everybody in the community, and it demonstrates the utility of NOAA data. And then in the cases of AI, demonstrates how NOAA has used the data to create a new application, which might be in part based on AI. And inside of NOAA, we need to make it a lot easier to click a button and launch such Jupyter notebooks into a sandbox where it's connected to the data and any documentation you might need to explore and build things. This is just like a mashup of the kinds of technology we're thinking and how we're going to bring it together. Basically, we're not writing all the Jupyter notebooks ourselves. They are contributed by NOAA community members who might be working with UCLA in some examples. And we're language agnostic. So Python, R, or you name it, we're going to work to be accessible to. That will be open this year, the GitHub. Here's the example. Let me just do a quick time check. All right, so I've got a few minutes left. This is just a quick example. So a product of NOAA's is forecasting forecasting and identifying dangerous rip currents on the coastline for to make sure people can make safe decisions about whether they should go swimming or not. And that's a really important product, as you can imagine. It saves a lot of lives. So this is an example of AI having been used to improve this capability. That's top right. That's a tweet from somebody at NOAA about the release of the product, and you can kind of see it. The animated GIF on the bottom here is the Jupyter notebook representing the lessons learned from the creation of that product. That is one of the examples that will be publicly available in our GitHub later this year. All right, now you haven't seen very much about space science yet, have you? So I want to spend now. I want to give you a few examples of the space science and geomagnetism, magnetic navigation work that we're doing at NOAA. And classic quote: "All models are wrong, but some are useful. Some are really, really, really useful." And it's just a reminder that observations and models have to be treated and have to be explored and well understood so that we can use them to maximum effect. All right, so first example, characterizing the sun with our geosynchronous satellite constellation solar ultraviolet imager instrument, or known as SUVI. And basically has 6 bands, and those bands are differently useful to detecting space weather phenomenology, like solar flares, coronal holes, quiet sun that doesn't cause space weather. And the team basically used this and simple random forest technique to create what we call thematic maps. So basically, on the left side, bottom left is the picture of the sun annotated with important features. And there's just a bunch of detail about how that works and how the clustering process worked. Thematic maps are public. Well, let me play the movie. There you go. All right, so top right now is the actual sun and an automated labeling of the solar features. It's publicly available on our GOES-R Space Weather page. I'll provide the slide deck with all the links later. And there's also public example code and a paper reference there. I'm going to go to the second example, kind of going from sun to closer to us. So this is now the same satellite constellation, but measuring the in situ magnetic field. As Dr. Chi here knows, is an extremely important measurement, super valuable to understand the global modes of the magnetosphere, for example. Well, we launched our new constellation with GOES 16 a few years ago. And on the left-hand side, labeled 0, you can see that has some interesting features there. And next to the next satellite launched, so it looks like a nice quiet day geomagnetic field. GOES 16 had some anomalies in the field, mostly thermoelectric effects and deflections caused by the navigation system. So when the thrusters fired, it affected the local plasma. The local plasma had a current in it that deflected the field. There were some thermoelectric effects. So when the sun or when the spacecraft magnetometers on a boom, there's 2 of them on a boom, when they are sort of differentially being eliminated by the sun, that also causes differential heating, and that was causing some issues. So that was a great example of lessons learned and using GOES 17 basically through transfer learning and long short-term memory, or LSTM model, to correct GOES 17 measurements. The deflection is, it's plus or minus 10 nanotesla or so for those scientists to whom that is extremely important. But if you go down to the PC wave time scale, you'll see all the waves there. And GOES-R series has 5 times the bandwidth for anyone interested. You get to see PC 1 through 5. Okay, this is a X Prize example, and I promise I'm almost done, and we can have Q&A if you want. So this is I think it was a great example of recognizing that inside of NOAA, we don't have all the talent, and we want to go to the broad community. So we worked with NASA, their tournament lab, and released an X Prize to the community to predict DST in an operational setting. So using the data as it comes right off the spacecraft, not using, say, the Omni data, that's also awesome, we all love, but rather using the exact measurements right off of ACE and right off Discover. And based only on solar wind, and the purpose is to be able to pull this into magnetic navigation models, like are in all of our phones, by the way. So bottom line outcome, we had 600 people participate, 1,200 models were submitted. We could never do that ourselves. And we are currently evaluating the top 5 or so for basically transitioning them into our magnetic navigation real-time model called HDGM-RT. Right-hand side there, there's an animated GIF of a Jupyter Notebook on the LSTM version, kind of the starting point version of this model. The best model was an ensemble convolutional neural network, so an ensemble of 5 models. Yeah, I'll leave that there. Oh, this paper is almost submitted. It'll be submitted hopefully in a week. All right, and then finally, so last example slide. But there's 3 examples on it, so I guess it's the last of with 3 examples. This is from a colleague in our field, Enrico Camparel. And there's 3 examples on the left-hand side. Example is of that group working to automatically characterize what features of the sun were likely to cause the solar wind that is observed just above the bow shock, or just 1% of the distance from us to the sun, so just a little bit ahead of us on the way to the sun. So that's that first example there. Again, there's a paper reference for each of these on this slide. The one in the middle is a new product that they are running at CU Boulder right now, and they're the Space Weather Trek portal. And that's to predict DST for 1 to 6 hours ahead. There's an example plot. And on the right-hand side is really exploring what we call gray box modeling. And this is to predict the surface time variation in the magnetic field. This is really, really important for the power, electric and power grid community, as those big variations can damage equipment essentially, and they can be caused by significant geomagnetic storms. So that's a gray box model. And those plots were comparisons of ground stations. They're using ground stations plus the University of Michigan geospace model to put that together. Okay, basically my last slide. There's a lot of opportunities, right? But probably you know about a lot more than even I do. So please tell me about them. To build community together, maybe communities of communities around artificial intelligence and machine learning research and application development. From research to operations, back to research. I'm in operations, you're in research. So we're working to try to get all the communities connected as much as we can to help us better meet our mission at NOAA for all of us, actually. I only touched on a couple examples. I kind of like this quote: "What is the best way to make an optimal use of both their physical understanding, so physics driven, and our large amount of data in the center system, so data assimilative, machine learning, et cetera. How do we combine those things optimally?" There's a bunch of references that'll be in the deck that I share. Ideas for career development, listen to all the mailing lists, and if you have any job announcements, send them to me too, so I can help you broadcast those. And then finally, a few events of recent interest maybe. So Machine Learning Helio was held about a year ago now, and I noticed that they have posted their presentation, so that's publicly open, free. AGU and AMS, I think it's behind a paywall, so if you did register and attend, go back and check out those sessions that you didn't maybe have a chance to look at. Lots of great sessions on trustworthy AI, lots of great sessions in space science at AMS and AGU. And then finally, we do a yearly NOAA workshop open to the public, and we bring people, we bring in insights from all over the world. So feel free to join us. It's free. and it'll be mid to late September. All right, I know I went over time and I apologize for that. Thank you.
Thank you for your talk. Now would be the time for question and answer. So if anyone from the audience has a question, if you could raise your hand and then I'll call on you and you can ask your question. Or you can just speak, whatever's easier. If no one has a question, I have a question. So you mentioned like trustworthy AI a bunch. Like what really qualifies like an AI as trustworthy?
Yeah, it's a great question. And it's an area of active research too, because it's trust for who. So just touching on it, maybe closer to how maybe we think in terms of doing research. It's about understanding how the machine learning model, if that's what you're using, was created. So it can usually traces all the way back to the data that's used. Were there error bars used in the creation of the model? Were there error bars even known about the observations to begin with? Sometimes there aren't, right? That just depends on the what kind of feature engineering was explored. That could be a correlation map. I showed an example, but I didn't mention it in here. And then kind of at the outcome of it, maybe you got this nice machine learning model. It seems to be super performant on your 4 case studies. We'll try it on some other case studies. How does it do then? And then you can also look and see what was the relative influence of the input features. Maybe you're using the solar wind. So we know BZ is really important. Was it equally important to say the solar wind velocity in the performance of the outcome of the model? So if your performance metric is a standard one like RMSE, root mean squared error, or something similar to that, then the question is, okay, what fraction of that RMSE is attributable to each of the features that were used to build and develop the model? I'm just giving one example. That's called permutation importance. There's a whole group of development tools out there, and there's some GitHub packages in the community being developed, like scikit explain, scikit learn. There's also a group who's working to develop one they call scikit explain, which brings together those explainable AI techniques. So trust, I think, is a bit bigger than that. There's 2 other places to go for information that's emerging now. Really, all the nation states of different countries are starting to develop their perspective on what they see as the elements of trust. So we have a couple of executive in the United States. We have a couple of executive orders from the White House, and we have an agency called NIST, and they are working on, and they've recently released their risk reduction framework. So AI.gov is the kind of the U.S. government starting point for our national AI initiative, and there's some resources there on exploring this and other topics. So yeah, I think it traces all the way though to the user community. What does it take for that user community to understand the product well enough to fold it into their decision-making process? Yeah, I guess I give one more example. If you built the model and it's intended for societal concerns like air pollution in areas, if that model is built with air from a community that's not relevant for the community that you're trying to deploy this on, say post-fire, after a fire, how does the air quality change? Then that probably would have some trust issues. So it's kind of like that. So from interpretable and explainable AI to what does the target community need to know and understand to use this in their decision-making process. Thanks. It was a great question.
Oh, I also had a question. I really loved the presentation, by the way. It was incredible.
Oh,
but I was
thank you.
wondering more about like I see a lot of times like online they talk about like incorporating science into AI, trying to like make the models more efficient. So like kind of leaning back to like what you're saying earlier about solar winds, does that really only happen on like choosing which data is relevant side, or could you like include like algorithms in the training process itself?
Yeah, there's a whole Alan, I see here. Thank you. Great question. Also, thanks for being.
Oh, no, it's, yeah.
Yes, there's a whole branch called so there's physics informed AI. So that's where physics is a strongly bounding the potential outcome. So you don't end up with a totally wild prediction that is physically unrealizable based on any phenomena we know today. So that's physics informed AI. There's a branch called that's basically machine learning informed physics. So if you have a physical model, you can also improve its predictive capability using data. It makes sense, right? We have a whole branch of data assimilative approaches. So I think, did that address your question?
Yeah, thank you. Yeah, that makes.
Yeah, check out the references. There's some really, I think there's a couple of papers. I think the one by Camporeal and maybe references there, and would be pretty, might get you to some other reading material that will be interesting to you.
Thank you. Yeah.
I have a question. You mentioned the 22-year cyclone project, and I'm wondering kind of what are the kind of hardware infrastructure requirements you need to like implement an AI, especially of that size, or what you can expect for like smaller programs.
Oh, I don't know. That's a really good question. I'm gonna write that down. All right, I need to have better metrics for what. So we like to use this terminology called on-prem, meaning what's the physical hardware your institution buys and operates. You can point at it. You can see the racks. So that's on premises. For our high performance computing, HPC. We also have the terminology like just using say commercial cloud opportunities to do your compute there. And then there's groups that try to hybridize that. So they might do some of the work out in the commercial cloud, and they might do some of the work on their local compute nodes. You asked the question of what are the metrics around what compute is needed for tropical cyclone, and I don't know the answer to that. I think that's a great question, Eric. I'm gonna take it down, and it'll be more. I'll look into that. I mean, we can ask our team, and if you are genuinely interested in this particular project, happy to address that offline and send you an answer once we. There's a couple of papers I can point you at. That's the first. That'll be the starting point on the creation of that TC primed product. So happy to. I'll send that back to Peter and Eden.
Yeah, that'd be great. Thanks. I'm also curious, like, does more giving like an AI more processing power like improve its ability to how fast it can go? Like what do you like limited, I guess?
Yeah. So so a bunch of ways to think about this from my perspective. Some models we have that are they're very good, but they use a lot of, maybe they're data assimilative and physics based, and they use a lot of compute that has a measurable carbon footprint, and we have to think about that, right? As our atmosphere is changing. So there's a whole field of study called ensemble, or basically it's what is it? I can't remember what it's called now. But basically trying to speed up different processes by training machine learning models and replacing some of the more expensive compute-wise models with these surrogate models. I think surrogate models is the term people usually use. So that's a very active field of research and also success. So I think hopefully, did that address your follow-up?
Yeah, that was awesome. It's really interesting. Thanks.
Yeah, check that out. There's a really interesting program in Europe called Destination Earth, which intends to basically build out digital twin systems for climate and extreme weather. And they envision that much of the internal machinery will be accelerated by AI techniques in order to be fast enough so that different kinds of users, scientists, and analysts supporting possible policy considerations, can run ensembles of scenarios very quickly enough with enough accuracy. And that's where AI will be probably very beneficial.
So you're like using the AI to improve the system in the AI It's improving
Yeah.
itself, I guess.
Yeah, exactly. So, I mean, there are times when you need the best answer, and there are times when you need a good enough answer really quickly. And then you can run many of those ensembles and potentially statistically combine those to get an almost equivalent, we'll call it a data-based answer to, a more compute expensive process.
Thanks. That's all.
Yeah, thank you. Good question. I had to think about that.
Justin has a question.
Hi, first of all, so great presentation. I really enjoyed listening to it. And so you mentioned that like NOAA was interested in using drones for collecting weather data. I was wondering, just like, do you guys build the drones and like the hardware for the drones yourselves, or do you outsource that work to like other organizations?
I think we mostly buy them, but NOAA's a big place, so I can imagine that we might have built some too. In a second here, I will find you a really cool video of a commercial sail drone exploring during really tumultuous weather in the ocean to kind of showcase the value of not sending humans to those places and instead sending uncrewed systems. So I'm not familiar with I'm not too familiar with us creating our own, but we've definitely created uncrewed observing systems for years, say that we drop out of airplanes in tropical cyclone situations in order to get in situ observation. So that's an example of that's called drop sonde. So we probably have created some of our own drones, but I think our main focus these days is on really buying them.
And then I have a follow-up to that. Like when you drop them in, how do you get the data back? Because I mean, I guess it's like a tropical cyclone. Like, are you able to obtain those uncrewed systems? Like, do they just fall in the ocean, or like do you somehow upload the data remotely?
Oh, it transmits back to the nearby, I think to the nearby airplane or some other receiving station. So that you have basically you modeled the environment. You've got radar observations in the environment. You've got satellite observations of the tropical cyclone environment, and now you have in situ. So you've got a plane hazardously flying through there with very devoted NOAA pilots, and you have and they try to take in situ measurements both where they are and at the profile. And so I think it radios back. It has GPS and all of the atmospheric sensor capabilities inside of it. They're not very big.
Okay, that would make sense.
I don't know what happens to them after that. That's a good question. They probably try to retrieve them, but I'm not sure how they do that. But they do get the measurements in real time because that's what's really ideally needed.
Yeah, I have a question for all the students. We have students from many different backgrounds in science and engineering, but overall, so Rob, what is your point of view? Because what type of knowledge, experience, or trait that you find very useful in new graduates, so that you encourage all students to try to develop or acquire when they're still in school?
Yeah. So I'm older. I went to school previously, and when I was going to school, we had to write our own. We didn't really call it machine learning. We had to write all of our own stuff, right? I remember doing fuzzy math. That was like the popular topic at the time, and we were trying to look at different weather scenarios and impacts to equipment. So what would what would I recommend? Well, I would say get as many, actually, I would say get as many kind of experiences outside of your classic classroom experience as you can. I think from CU Boulder, and probably I'm assuming at UCLA too, you have probably more practical experiences available to you than I might have had. So taking advantage of those, like we have student-led CubeSats that are in space now, right? From students at universities, where they manage the entire program, the entire project, through a series of years. So each year, that cohort of students contributes in their way. So I would say get as much diverse experience as you can, and try out some fields of interest. That would also be really useful, I believe. So we have hackathons every year. I think we probably have one like right about now, looking at some NOAA problems in a collaboration and partnership with NVIDIA and NCAR. So maybe see if you can engage in some of these hackathons. Those also didn't really exist a couple decades ago, dating myself here. So I'm in love with hackathons. So I would check those out. And another thing I would have loved to do, which I did a little bit later, is consider contributing to community tools, either developing them or testing them, depending on what your skill set is. So developing community tools and or participating in AGU's got an ethics program going on right now where they're seeking feedback and inputs. And I'd say if you can get involved in some of those community activities to help co-chair a session or help facilitate feedback from the community, that might also be really useful too. And I guess the last thing I would share, sorry, we keep going here. And it was something my advisor recommended to me. And that she said, try to support the needs of a proposal review panel, if asked. Because she said, you won't learn how to write a proposal any better than reading a lot of other proposals and seeing how that process works. So that was, and then I guess, okay, I thought of one last thing, I promise, only last thing. Seek mentors. And seek one, and don't be afraid to change mentors. And you might even have more than one. It depends on your, the different aspects of your life that you want to be able to vector check your thinking on. I have a mentor, and it wasn't until much later in life that I recognized the value of that. I mean, I've had thesis advisors and whatnot, and they were mentors, yes, but more of a life mentor. And I have one at NOAA, and I think I'll probably do that forever now because it's just a really excellent relationship.
Great. Well, that's great. Thank you so much, Rob.
Well, thank you. It's a little on the fly. I appreciate it. I love to think about I love to think about the hard questions that you and your students have posed. They're the most fun.
I've got another question about your presentation.
Okay.
At one point you talked about like using NLP to determine, I think you said if like how much your other AI helped like the community. Am I right saying that?
There's lots of ways. Yes. Not wrong. Yes, right. And let me add a little bit of context. So we have a project. I'll try to find a link to it. It's part of a bigger project, and it's called Show Us the Data, basically. I think mostly led by Census, perhaps. But anyway, I'll find the link for it. And our contribution at NOAA is essentially to try to understand the value of our investments in observing systems and curating the data products that are used in, for operational weather forecasting, but also used for the research community, like at UCLA, to better understand through their use in this particular example, the use in the peer-reviewed peer-reviewed journals. So if you think about it, the peer review process is pretty rigorous, and journals that have a high impact score tend to have a pretty rigorous process to help submissions mature themselves, or maybe they're not ready for this journal kind of thing, but help mature themselves. So once something gets published, that's basically like an excellent training data set. So using NLP, natural language processing, this program endeavors to identify the value of the data that is cited within the papers, from across the spectrum of, okay, the data was just called out as an ancillary detail, but it doesn't really, it's not critical to the conclusions. So what is the semantic value of that data in informing the conclusions of this paper? And maybe it's a paper that now has become highly cited, and it's been vetted from all sorts of independent other efforts. So that's just one a particular example that we are contributing to. I'll find a link to the overall program. I'll put it in the chat here.
Okay, what was the name of it again?
I think it's Show Us the Data.
Show us the data. Okay.
Yeah,
It sounds
I have it. Yeah, I have it written down. And it's led by the Coleridge Initiative. At least that was, oh, here's a good, I'll put one link, and then I will probably, just to start you off. I think that might have been from a 2-year ago part of this effort, but let me just put it in there to get started. Oh,
okay.
Thank you. One of my colleagues already did it. Excellent, thanks, Heather.
Okay.
So yeah, Heather, who was also a past rotational assignment deputy for our Center for AI. So that's a good starting point for that larger effort.
Okay, thank you. Sounds really interesting.
Yeah, and I didn't put my email on the leadoff slide, but it's rob.redmond@noaa.gov, and it'll be in the PDF that I create that people can have. So if there's any questions about this presentation, or people think of something different, or want to learn more about NOAA or what we're doing with AI at NOAA, feel free to reach out.
Anyone else have questions? Hearing none. Thank you so much, Dr. Redmond, for coming and speaking to us. I think we all got a lot more knowledge, and I'm excited to look into this more.
Cool. Well, check out NOAA student and recent graduate opportunities by looking at our Office of Education. And also, if you have an interest in us in general, we'll try to keep a good tempo of opportunities that we hear about in our mailing list.
Great, thank you.
So thank you again. Yeah, thank you so much.
Yeah, thank you, Rob, and yeah, thank you so much for joining. And also I'd like to thank Heather for joining as well. Yeah, we really appreciate your talk today and telling us so much. Yeah, we wish you in your new center, very success, and we look forward to the upcoming activities that we can learn more from you and your center. So thank you.
Thank you very much. You're all very kind, and thank you for the great questions.